Just wanted to make a quick little video discussing the properties of a hexagon. So I quickly just drew a hexagon. I just made points. I just reproduced the hexagon that I made in the previous video, which is a 3-inch diameter from point to point. So all I did here was I just marked 3 inches, and then I marked 1.5 inches to get the center point. And then from that center point, I arced above here and here and here and here. And then I moved my compass out to this point and marked here and here, and then this one and marked here and here, which basically gives me the 6 points of that, because each side length is now equal. Basically, I just drew 4 equilateral triangles. The first 2 emanating from this point and this point, and then the second 2 equilateral triangles from this point and this point. And then instead of drawing this down to connect to the center, I just connected across the top, which is the same side length because of the equilateral triangle. So that's just quickly how I constructed that. But I want to talk a little bit about the parts of this. So if I were to draw a line, and this one line I'm not going to draw right down through, but if I draw a line from point to point, right, I'm going to stop this one there. It'll make sense later. So I'm just drawing a bunch of lines here, point to point, and we're going to create our series of right-angled triangles. Well, all of these angles inside here, right, they're all equal. And they're what's called an apex angle, okay? So theta is representing an apex angle, right? That's the angle in the center. It's not an internal angle. That'll be discussed later. This is what's called an apex angle. So if I were to say, come out to the outside of this shape, I'm going to switch rulers because I got a lot of spinning to do here. And I just connect each of these straight as if they're continuing on out this line. And I'm just going to kind of create that little pinwheel effect coming around this to show you what comes off of every side. And just with a bunch of little hidden lines. So, and this works for any regular polygon. Okay, it's not limited to just a hexagon. Let's do the last one here. Right, so these angles out here, I'll label them with an X. These angles outside here are what they call external angles. Okay, so X, they are external angles. Right? And the interesting thing here about these is the external angles are actually equal to the apex angles. So the apex angle is equal to the external angle, and the sum of those, so basically the sum of all the apex angles is equal to the sum of all the external angles, which also means that these all equal 360 degrees, right? So in here we have 60-degree angles, and there's 6 of them, which equals 360 degrees. Now, because these are the same angles out here, these external angles, 60, 60, 60, 60, 60, 60, which is 6 of them, which also equals 360 degrees. So in some of the math problems you may be given and stuff, depending on what you're given, just know that the corresponding external angle is equal to the apex angle. Okay, so they're related. This is only true for regular polygons, not true for irregular polygons. Right? So now I am going to draw a little arc here, just to connect that missing part of the line here. So I'm going to arc from one of these sides right over to the other, right? And this here, I'm going to label this as an A, and what this is what's called the internal angle. And there's lots of fancy formulas to figure out what this internal angle is, but when we're talking about a regular polygon, this internal angle here will quite simply be 180 degrees, the sum of a triangle, the sum of all the angles in a triangle, So 180 minus that apex angle. So to ever find the internal angle here, all we have to do is just take 180 degrees and subtract that apex angle. And that will give us that internal angle here. Okay? Because in a regular polygon, all the triangles that make up a regular polygon are all the same size. Right? That's why this works for every single one of them. And it also is convenient here that the internal angle is 2 mitre angles. So if I take my compass here now, and I set up on this point here, I'm just going to shrink it up just a little bit, and I draw an arc from here, right? So this angle, the angle at the base of the equilateral triangle here, let's label this with a B. This is what's called a mitre angle, right? So this is the mitre angle here. And all the internal angle is it will equal 2 mitre angles. So if we ever need to find the mitre angle, all it would be the internal angle, right? So A, whatever's left after we take the apex angle away from 180, and we just divide that internal angle by 2, which would then split up and give us 2 B's, which is our mitre angles. Right? So imagine this line continuing here, and we split that in half. In this triangle, A is equal to 120 degrees, right? Because it's the 60 subtracted away from 180, the sum of the triangle, which leaves us with 120 degrees. So that's our internal angle. And if I split that internal angle in half, that means that this triangle here, or sorry, this angle here and this angle here are both equal to 60 degrees, 120 divided by 2. So we would have 2 mitre angles here, both equaling 60 degrees as well. Okay. Now there's another interesting angle here, which is very specific to carpenters or cabinet makers or anybody else. But if I had a problem where I wanted to put some trim around the outside of this shape, sorry for the small scale of this, but if I had some trim that I wanted to put around the outside of this, I have to know what angle I'm going to set my saw at to make this cut right here. Right? We know that this angle left here is 60 degrees, right? Because this line just carries out here, and then this line here is just parallel to that one. So we know that this here is a mitre angle of 60 degrees. But you have to remember that the saw that we use, and I'll just slide this up here, if I have a saw set up, right? So this is, say, the fence, and then perpendicular to that, right? Forgive my cruelty here if it's not exactly perpendicular. Perpendicular to that, we have the saw, right? So we have the fence, and then we have the saw. Well, we label the saw as 0 degrees, right? So when we're cutting, but in actuality, that's not technically correct, because when we set our material along the fence, we're actually cutting 90 degrees to this back edge, right? We're cutting 90 degrees to this back edge, but it's labeled as 0. And if you look at this piece, if I set this piece up along the fence here, when I take that angle back in, I want to be left with that 60 degrees, right? Because that's that angle that I want that piece to be left with. So in order to do that, right, I have my piece of lumber coming out here. I'll draw this one in, say, blue. I should draw it in green to match, but that's okay. So I have my piece of trim coming across here. When I actually set the saw up and I bring my material back through here, this angle here must match the mitre angle, right, of my piece. So that means that the angle right here, let me just draw a nice smooth arc so we can see it. This angle right here that I'm left with is my mitre angle, and I want that to remain at 60 degrees, right? So this piece here is going to be cut, and I'm going to be left with 60 degrees. But the trick here is that's what I want to be left with. So what I'm actually going to set my saw at here is I'm going to tilt my blade to this same angle that's coming through the piece, right? So I turn my blade over here, right? I turn my blade so that I'm left with 60 degrees. But because this here is already set to 0, when I turn this, I'm only turning 30 degrees, right? So I turn the blade to 30 degrees and I make the cut because this is 0, right? If this were 90 and I turned, I would be counting down, which would leave me with 60, right? This corresponding angle over here is also 60 degrees, right? Unless I drop this perpendicular down there where the piece would be cut, then this angle inside there would actually be 30 degrees, which is what we actually cut off the material. Because the idea here is we want to be left with the 60 degrees to satisfy the mitre angle of this hexagon. But with the saw and the way it's set up, we actually have to remove the opposite of that. We have to remove the 30 degrees to be left with the 60. So we would actually set the saw mitre angle to 30 degrees to make a 60 degree cut like this, to do the trim around a hexagon. And this exact same theory applies to any shape and any number of divisions that you want to do to create a mitre angle along a curved surface. All right, we just have to take that shape and find that mitre angle. And then for the mitre saw setting, two T's there. For the mitre saw setting, we are going to take the mitre angle, which is B here, away from 90, right? So I kind of wrote that wrong there, sorry. It's going to be 90 degrees minus that mitre angle. And that will be the saw setting that I would need to cut to create that piece of trim that's going to go around the outside. And that is kind of the bulk of what makes up the regular polygon. Just a couple more things. Here quickly is the diameter of a regular polygon. So that distance right across the center. Also called point to point. So this line here would be point to point. Right? We also have a distance right here, like I explained in the last video. If I cut a line through here perpendicular to one of the sides and perpendicular to the other side, so a straight line, this one here would be side to side. And you got to be careful because the side to side measure would not be the radius of the circle that would enclose this shape or circumscribe this shape. This is perpendicular. This is not a radius. This would be the height of our triangle, right? Which we could use trig to figure out based on these angles and these side lengths if we needed to, right? But when you're constructing this shape, if you're given the side to side distance from here to here, you must go about constructing this a little different to maintain that distance, right? Because this side here is unknown and this side here is unknown. So we can't just use the regular draw a circle and then step off it when you're given the side to side measure. So you have to start a little bit different and think a little different, which we'll go over in another video. Okay, and then the last type of line you could put here, which I could theoretically give you, would be like, I'll draw it down here. It could be a weird one, tricky to do, but technically we could do like a point to side type of distance, right? It'd be infinitely more complex to construct this, but this one would be point to side. Okay, I may explore that in future videos, but for now we're going to kind of leave this one alone geometrically. But so most of what we're going to be giving is either, well, also there's one more too, but I'll just go through these first. Mostly we're going to be giving the diameter or a point to point measure of the regular polygon, or I may provide you a side to side distance of the regular polygon, or the other one is I can just give you a regular side length of the polygon. So if I just switch color up here and I can pick any one of these sides, I could just provide you with this side length, right? Or problem you may be faced with, right? And that side length could also be used to solve to draw this shape. So point to point, or the diameter, a side to side, or a side length. Those are the most common ways to give information to construct any regular polygon. And then one that's a little bit more complex would just be the point to side, right? That one's a little bit trickier, especially if that point, the side here isn't in the middle, like you're giving some other distance, then you'd be into some trigonometry to help you solve for the answers of this, right? So that about sums up the regular polygon. Now remember, this holds true for any regular polygon. All the apex angles will always add to 360. The external angles will always equal the apex angles. The internal angle will always be 180 taken away from the apex angle. 180 minus the apex angle. And then of course your mitre angle will just be the division of A in half. And that'll be your mitre angle. And then if you wanted to set up a mitre saw to cut two pieces to fit that angle, right? So two pieces to join here and fit that angle right here, you would have to then take 90 degrees and subtract that mitre angle, so we can successfully make that cut to be left with that 60 degrees that are required of that triangle. Okay, and that sums it up.